China didn't steal chips or copy GPUs. It dug up a 100-year-old idea and just flipped the entire AI race upside down. A forgotten computing method just came back with terrifying force, reshaping AI, energy, geopolitics, and why GPUs are hitting a wall.
They're going to take that capability because the United States is no longer participating in China. We've left China. We're evacuated that market. We've conceded that market. And so now they've got to go build their own.
And this is where things started getting uncomfortable. 3 weeks ago at the Financial Times AI Summit in London, Jensen Huang stood on stage and said something nobody expected to hear from the man behind Nvidia's empire. Not a critic, not a rival. The guy who built the GPU age itself. China's going to win the AI race. Not might, not could, will. You could almost feel the room tighten. This wasn't a hot take. This was a warning. Nvidia's entire dominance, every H100, every AI data center, every trillion-dollar valuation rests on GPUs being the future. And here was the CEO admitting out loud that the current path is breaking. Why does this matter? Because GPUs are hitting physical limits. Power consumption is exploding. Data centers are sucking electricity like small cities. Training a single large AI model now costs millions just in energy. That's not scalable forever. So when Jensen Huang says this, it's not drama. It's a signal flare. A moment where the industry quietly realizes the old playbook is running out of pages. Have you ever seen the leader of a winning team admit the game is about to change?
China.
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 Now here's where the story usually goes wrong. The lazy explanation is, China copied the West again. That's the headline people want. It's simple, it's comfortable, and it's completely wrong. This isn't a stolen IP. This isn't reverse engineering Nvidia. This isn't about catching up on smaller nodes or better lithography. China didn't chase the GPU race. They walked off the track entirely. What they did instead was reopen a problem Western engineers abandoned decades ago. Not because it was uninteresting, but because it was too hard, too unstable, too messy. Analog computing. For over a century, it was written off as a dead end, a historical footnote, something that almost worked but never could. And that's exactly why sanctions didn't matter here. You can't block exports of an idea you stopped believing in. While Washington was tightening restrictions on digital chips, Beijing was quietly rebuilding a different foundation altogether. So ask yourself, how do you sanction a future you didn't see coming? Before zeros and ones ruled the world, computers didn't think in steps. They flowed. Early analog computers didn't break reality into bits. They worked with continuous signals, voltages, currents, and physical movement. The math looked more like nature itself, smooth, fluid, real. But there was a catch, actually several. Noise crept in, signals drifted, errors stacked on top of errors. A calculation that started clean would slowly fall apart. The longer it ran, the worse it got. Engineers fought it for decades and eventually gave up. Digital computing won because it was boring, but reliable. Ones and zeros didn't drift. Transistors are either switched on or off. You could correct errors, reset states, and scale systems without chaos creeping in. So for 100 years, analog computing was declared dead, a failed experiment, something you read about in old textbooks, right next to vacuum tubes and punch cards. No one seriously tried to revive it, because everyone agreed it couldn't be fixed. Or at least that's what the West believed. And here's the question that should make you pause. What if the problem wasn't analog computing itself, but the tools we had back then to control it? Because that assumption just collapsed. And here's where the story stops being theoretical and starts getting scary. On October 13, 2025, researchers at Peking University published a paper in Nature Electronics. Not a blog post, not a leaked slide deck, one of the most respected journals in hardware science. The title sounded harmless at first. Precise and scalable analog matrix equation solving using resistive random access memory chips. Translated into normal language, we fixed analog computing and made it outperform digital systems. That sentence alone breaks a century of assumptions. Analog was always faster but never accurate. Digital was accurate, but slow and power-hungry. Engineers believed you had to choose. This paper said, you don't. The team demonstrated analog computation with accuracy matching 24-bit digital systems, something many believed was physically impossible due to noise and drift. That wasn't a small improvement. That was a wall getting smashed. This isn't shaving 10% off latency or squeezing more transistors onto silicon. This is changing the rules of computation itself, a foundation-level shift. If digital computing were the industrial revolution of information, this is discovering that electricity runs cleaner in a completely different direction. And the worst part? They did it using old manufacturing technology nobody bothered to sanction. Okay, this part sounds complex, but stay with me. It's actually beautiful once it clicks. Traditional chips, CPUs, GPUs, everything, work in binary, ones and zeros, on or off. A transistor is either conducting electricity or it isn't. That's it. Now here's the hidden problem most people never hear about. Your data lives in memory. Your calculations happen in a processor. Every operation means shuttling data back and forth between the two. Constant movement, constant energy burn. This is called the von Neumann bottleneck, and it's why modern GPUs guzzle hundreds of watts. China's analog chip attacks this at the root. Instead of separating memory and computation, it uses resistive random access memory, RRAM. The same physical device stores data and computes with it. Think of it like this. Normally, your fridge stores food and your stove cooks it. You're constantly moving things between them. Now imagine one device that does both. Raw ingredients go in, cooked food comes out, no movement, no waste. That's in-memory computing. But here's where it gets wild. RRAM doesn't store data as ones and zeros. It stores data as resistance levels, hundreds of them. Binary is a light switch. RRAM is a dimmer. When electricity flows through these memory cells, the resistance naturally performs math. Multiply, accumulate, all at once, across thousands of cells, in parallel. No clock cycles, no instruction queues, no waiting. The physicists do the computation for free. That's not clever engineering. That's exploiting reality itself. So how does this stack up against the king of AI hardware? Nvidia's H100? The researchers tested their chip on matrix equation solving. That's not random math. That's the backbone of AI training. Every neural network lives and dies on matrix multiplication. The results were uncomfortable. They reported up to 1,000 times higher throughput compared to an H100 in the same task. 100 times better energy efficiency, and accuracy equivalent to 24-bit fixed-point digital systems. Now pause for a second. These aren't marketing slides. These are lab benchmarks, yes, but they're peer-reviewed benchmarks. And even if real-world results land at a fraction of this, it still reshapes the industry. And here's the detail people miss. This chip wasn't built in some exotic lab with impossible processes. It was manufactured using commercially available production methods. That means scaling isn't a fantasy, it's an engineering problem. And those are solvable. So ask yourself, what happens when good enough beats best in class by orders of magnitude? This is the part Jensen Huang warned about, and almost nobody listened. Between 2022 and 2025, the US banned exports of advanced GPUs to China. No H100s, no A100s. The idea was simple: starve China of computing power, end the AI race before it really starts. But Huang said publicly that this would backfire. Cut off the supply and you don't kill innovation. You force reinvention, and the data backs him up. Multiple studies show that once Chinese firms land on US sanction lists, something strange happens. Government funding increases, private investment follows. R&D spending spikes. Huawei is the blueprint. After export controls, they built their own operating system, their own chips, and grew their telecom dominance. Sanctions didn't stop them. They changed their direction. And analog computing is the clearest example yet. You can't sanction something you never pursued yourself. While Washington was guarding yesterday's technology, Beijing was building tomorrow's. This wasn't defiance, it was an adaptation. And adaptation always wins in the long run.
According to researchers from Peking University, the device could work 1,000 times faster than top digital processors like Nvidia's graphics processing unit.
And now comes the part where this stops being academic and starts becoming strategic. 6G networks. Next-generation wireless relies on massive MIMO, hundreds of antennas processing signals simultaneously. The math is brutal. Current digital chips struggle to do it in real time without a massive power draw. Analog RAM chips thrive here. Ultra-low power, instant parallel processing. Suddenly, 6G base stations don't need power plant level energy budgets. AI training acceleration. AI training is matrix multiplication on steroids. That's it. That's the whole game. These chips were optimized for second-order optimization algorithms, the cutting edge of training efficiency, the kind that determines whether a model trains in months or days. Imagine training a GPT-scale model with 100 times less electricity. That's not faster than AI, that's cheaper dominance. C, edge and autonomous AI. This is the real wild card. Because these chips sip power, AI no longer needs the cloud. Training and inference can happen on device. Phones, cars, drones, medical wearables. No data leaving the device. No latency. No centralized control. That's not just technological power. That's strategic autonomy. And China isn't waiting.
The real AI race is happening in outer space, orbiting above us at 28,000 kilometers per hour. Take any tech giant you know, Amazon, Google, OpenAI, they aren't just competing for users. They are racing to build something that humanity has never attempted before.
Here's the truth nobody likes saying out loud. The AI race isn't about chips. It's about electricity. In the US, data centers are straining aging grids. Power prices are rising. Entire regions are pushing back against new AI facilities. Meanwhile, China is doing the opposite. They're subsidizing energy for tech companies, cutting costs by up to 50%. But there's a catch. Those subsidies apply to domestic chips. Now layer analog computing on top of that. When your hardware already uses 100 times less power, cheap electricity turns into an unfair advantage. Training that costs millions in the West costs a fraction in China. AI progress becomes easier, faster, cheaper. This is why analog computing is dangerous. Not because it's faster, but because it breaks the energy bottleneck entirely. Digital systems waste power moving data. Analog systems turn power directly into math. Physics wins, every time. And this brings us to the uncomfortable ending. Western chip makers aren't asleep. They're busy, but they're busy optimizing the past. More transistors, bigger GPUs, higher power envelopes. Nvidia, Intel, AMD, different logos, same philosophy. Scale harder, push further, burn more watts. Meanwhile, analog and photonic systems are treated like side projects. Research curiosities. Something to watch, not bet on. China made a different choice. They asked, what if the problem isn't scaling, but the model itself? That philosophical split is everything. One side is squeezing blood from silicon. The other is rewriting how computation happens at all. And once paradigms diverge, catching up isn't about money, it's about mindset. The GPU era isn't dead, but it's no longer alone. Analog computing just proved the future of AI won't be decided by smaller nodes, but by smarter physics. China saw that first. So what do you think? Breakthrough or overhype? Drop your take below, and if this hits, like and subscribe. More is coming fast.